Good morning. My name is Jaron Kelleher. Today I'll be going over a project I did this semester on mimicking art with a Wasserstein-GAN with gradient penalty network. Let's begin. So, as I said, I'm looking to recreate the art of Nicholas Roerich using and comparing different multiple network types. In this presentation, I'll be comparing the standard GAN, the deep convolutional GAN, the Wasserstein-GAN, and the Wasserstein-GAN with gradient penalty. A little bit of history behind GANs. They were made popular in 2014 in a paper by Ian Goodfellow, and that's really where the GAN terminology started. These networks pitted a generator network against a discriminator network in kind of a game of cop and robber, where the generator is more like a counterfeiter trying to make fake checks, and the discriminator is more like a cop trying to determine if the check is real or fake by comparing those fake checks to real checks. So as you can imagine, as the generator gets stronger and starts producing more real-looking fake checks, the cop also needs to get stronger and learn to tell the difference. So around and around they go, and that's how these networks work. The discriminator gets stronger, which in turn makes the generator get stronger, which in turn makes the discriminator get stronger, and yada, yada, yada. Since then, there's been quite a bit of improvements to generative adversarial networks. We'll be going over 3 of those today and comparing their results with the original GAN network. So existing, as I said, the original GAN was a simple feed-forward, fully connected neural net. The discriminator had an output layer that was a sigmoid output layer, so essentially just saying whether the image was real or fake, and the generator has a tan-H output layer. The loss function of this type of network is a binary cross-entropy loss function, and really the benefits of this, it's a simple network, quick to train. However, it does have its pitfalls. One problem is a diminishing gradient, where if the discriminator gets too strong, the generator stops learning, and it can't learn anymore. Another problem is mode collapse in GANs, and that the generator learns only one distribution of the data. And I'll show what I mean by that in my Gaussian mixture model dataset later in this presentation. After the standard GAN came the deep convolutional GAN in 2016. These GANs introduced convolutional neural net architectures to the standard GAN, so rather than having your simple feed-forward, fully connected network, we now have layers of convolution and deconvolution layers in our network, along with batch normalization. So it's really taken some of the expert convolutional neural net architectures and applying them to these generative adversarial networks. Now it still kept the sigmoid output function and still used the binary cross-entropy loss function. So it maintained the weakness of mode collapse, and that the data could still learn only one type of distribution and fail to learn others. But you get a stronger discriminator and generator with the use of convolution and deconvolution layers and batch normalization layers in the network. From there, Wasserstein GANs were introduced, and those were introduced really to eliminate that mode collapse problem and the stability problem when generating and training these networks. So it was produced originally in 2017 and proposed by Arjovsky and a couple other authors, and it replaced the sigmoid output layer of the discriminator with just a linear layer. So it really transformed the discriminator into a critic. So usually in the Wasserstein GANs, the discriminator is referred to as the critic of the network. Otherwise, generally works the same. It has a different loss function, which is now the Earth mover distance of the network when you send in real data and fake data, also known as the Wasserstein distance. It's the average of the real data output from the discriminator minus the average of the fake data output from the discriminator. So very simple. They found that the RMS prop algorithm was a proper optimization algorithm when using the Wasserstein GAN network. And then from there came the Wasserstein GAN with gradient penalty. So this tries to tackle an issue seen in the Wasserstein-GAN that I failed to mention, which is weight clipping. So essentially with Wasserstein-GAN, the original one, you had to tune another hyperparameter, a weight clipping parameter, to the network. If you didn't, then you could see your weights start to explode, which caused either vanishing or exploding gradients on your network, which led to instability. So you had to learn that other hyperparameter with the Wasserstein-GAN. With the gradient penalty, however, that removes that requirement of needing to do any clipping. It applies a penalty to the gradient of the function while learning. So the loss function is modified in this network to include this gradient penalty term at the end, as you'll see here at the bottom of the slide. And now the loss is equal to the negative Wasserstein distance of the network plus this penalty times a lambda. Generally, the lambda is 10 for this network, and when calculating the penalty, you're no longer using just the real or the fake, you're using the real and the fake, or rather a combination of the two with some epsilon number to combine the data, and that's what you're using to calculate your gradient penalty. And what this did, this introduced real stability into the training of the network so that you're no longer getting mode collapse, you're no longer getting any type of vanishing gradient or exploding gradients on the network, and it allows the generator and discriminator to always train. With one drawback, the gradient penalty is very computationally expensive for the network. So it could double, as much as double, your processing time and training time just to get the network trained. And it takes longer for the network to converge as well on an output. And you'll see some of that in the next slides. So now we'll go into our performance evaluation. The standard GAN performed not so well on either the Gaussian mixture model or the ARTIST dataset. I'll show you the ARTIST dataset on this slide here. As you can see on the very left here, we have the highest rated ARTIST fake images from the discriminator, and then to the right of that are the highest rated real images from the discriminator. And as you can see, for the fake data, a lot of them are very similar and are the same, right? There's not much difference. If you look at row 2, 1, 2, 3, and 4, column 4 are just about the same image, right? So there's no variety here. And on the right-hand side, what I show is the same noise variable sent into the generator over many epochs. So you can see about halfway through, the generator really collapsed on one style and never got out of it. So the GAN did not perform very well on this ARTIST dataset. DC-GAN performed a bit better. We'll just move on to slide 13 here. So you can tell right away there's a bit more variety into at least the highest rated DC-GAN networks. And on the left, so you'll see kind of a standard style throughout, but the contents of the imagery are a bit better, right? There's a little more variety in the contents of the data. However, if you look at the right is a sample set of data with just random noise data, and if you look at column 1, rows 5, 6, and 7 all have roughly, it's the same image, essentially, and you'll see that same image throughout the grid. So the DC-GAN, though it gave us a higher variety, it still suffered from mode collapse with the data set, and it started outputting really the same type of data for many different input variables. We'll move on to the Wasserstein-GAN on slide 15 here. The Wasserstein-GAN actually performed really well in variety. So if you look on the left-hand side, those are the highest rated fake data and the highest rated real data. So as you can tell, the discriminator kind of collapsed to a specific style as rating it as the best. So that didn't work out so well. Further study needs to be done on why that happened and why we can prevent it. So because of that, the highest rated fake data also had that same style. However, if you look at the randomly generated data with random noise samples, I think that's where this really shines. You see some beautiful art, I think, and imagery in this data that really looks like it could have come from Nicholas Roerich and some of his scenery images later in his career that I think are very convincing to me personally. And then finally, the Wasserstein-GAN with gradient penalty performed even better than that of the Wasserstein-GAN. So if you look on the left-hand side here, again, the discriminator chose a wide variety of real data as its highest rated. So it didn't really stick to one style there. Now, unfortunately, the fake data here for its highest rated did have the same style, but you can tell within there, there's some very high quality, I think, images that maybe with a bit more training would have come out even sharper than they were. So row 1, column 1, clearly identifiable as a person in there. Row 1, column 7, also you can clearly identify the person in that image. And there's quite a few other images of scenery in there that are identifiable. Row 7, column 3 is another great one with a person in it. Unfortunately, when you look at the randomly generated noise data from the output, it didn't turn out so well. It's a little bit more blurry than the other one. I suspect this is due to lack of training, and the network just needed to train longer in order to fine-tune its output. But even with those, you can still see the imagery starting to form and really some of the shapes starting to form with the Wasserstein-GAN with gradient penalty. So I think it performed very well. No mode collapse in any of these images. They all look pretty different. And I think with further training and more time, this would have performed even better than the others. Slide 18 is our Gaussian mixture model results from the data. So I trained the GAN, the Wasserstein-GAN, and the Wasserstein-GAN with gradient penalty on a Gaussian mixture model with 3 blobs, all with a tight variance. And as I said before, a mode collapse, this really demonstrates that on the left-hand side, you have the original GAN, and it collapsed to 2 distributions. It didn't even learn the 3rd distribution. That's really one of the problems with the original GAN architecture. However, the Wasserstein-GAN with gradient penalty did not suffer that same thing. They both learned all of the distributions, and the gradient penalty GAN even had a tighter variance than the original Wasserstein-GAN. So I think it performed very well. Now, the one drawback of the Wasserstein-GAN and the Wasserstein-GAN with gradient penalty are the training time. So all of these networks were trained for the same number of epochs. However, you can tell the gradient penalty calculation just incurs such a huge time cost on training that it is really not preferable. And if there are other methods to stabilize training in order to get it done quicker, or if you have a much more powerful network, you can stick with the gradient penalty. But otherwise, if you can find a way around it and can still stabilize and prevent mode collapse, that would definitely be preferable. So in conclusion, all networks but the standard GAN network performed okay. I think the Wasserstein-GAN output the best imagery in terms of what looked like the original artist. The one with the gradient penalty performed the best. The Wasserstein-GAN without the gradient penalty, to me, was second best. Still had a little bit of mode collapse in its data. Some of the images looked similar, but otherwise had much larger variety and output some very nice imagery from the artist. The deep convolutional GAN unfortunately suffered from mode collapse, so really the sigmoid output layer is what hurts it in that network. And then the standard GAN network suffered from mode collapse completely and didn't even learn the artist data. So my final thoughts on this, if you had to pick one, I would pick the Wasserstein-GAN and try to learn the weight clipping parameter, or just pick the Wasserstein-GAN with gradient penalty. That way you don't have to worry about that weight clipping, but try to make sure that you have the processing power to handle that amount of data, because it's a lot and it's a lot of computation. And now we will go to our code on the network. So I've created a couple files here. The main one is main.py, and this really is what trains the data and trains the art. So I have multiple data sets here. You can either train with the artist data set, or you can train with CFAR10 and choose your index. I did one in my white paper, the dogs data set with the gradient penalty. I think it performed pretty well. So with the data here, you know, Python space main.y, you've got all these arguments here. You can choose your model, your output directory, what type of data you want to choose, your CFAR index if you choose CFAR10, how many epochs you want to train with, your noise size, whether or not you use CUDA, which I recommend you do. Little story, training computer at home without a CUDA processor took about over a minute per epoch. I found a PC with a CUDA processor and dropped it down to about 1.5 seconds per epoch. So very, very large speed increase if you do use a GPU. Clip value, if you're using the standard Wasserstein-GAN and your critic iterations. So the Wasserstein-GANs use about 5 or more critic iterations per generator iteration. The other two use just one-to-one. You can select your output rate and your batch size as well. Now I think I've combined the models pretty tightly. I used relatively the same network between the deep convolutional GAN and the Wasserstein-GANs. They just had a different output layer. And the deep convolutional GANs also did not use a normalization, or the deep convolutional GAN used a normalization layer. The Wasserstein GANs did not in its discriminator network. So these are the networks here. Here's my generator. It's just if we're using the GAN, it's just a linear layer. Otherwise, we got transverse convolutional occurring between them with a tangent H output layer. And then the discriminator, like I said before, if you're using the DC-GAN, your convolution with batch normalization, and then except on the first layer, there is no batch normalization on the first layer. And then for the other networks, the Wasserstein-GAN, there is no batch normalization. And then finally, the standard GAN is just linear layers all the way through. I created a generic trainer class that runs the training for all of them. It is assumed with this trainer class that the GAN network will contain a discriminator, a generator, a discriminator optimizer, generator optimizer, a function that gets a discriminator loss, the generator loss, and a post-step update, which many of them, there is no post-step update. However, in the Wasserstein-GAN, the post-step update is a clipping of the weight parameters in the discriminator. So these are the networks that I created. The Wasserstein-GAN with gradient penalty, as I said, it occurs this additional penalty calculation seen here. Really another thing I did for optimization with the data that really sped it up is when I'm getting my data, I'm transferring. If I know I'm doing multiple critic iterations at once, I'm generating all of my fake data and getting all of my real data for each critic iteration and transferring that to the GPU all at the same time. That way you're not transferring small chunks of data, you're transferring large chunks of data, which makes your process and training time go down. After that, I wrote a couple utility programs. So that main one outputs grids and sample imagery every about 500 iterations is the default, but you can do it every 200 or 100 depending on what you set it to. And so I wrote some utilities to go through that and gather some good information out of it. So as I said before in my model, I had a generator evolution grid which kept the noise value constant and then fed that into the generator network over many different epochs to see how the generator is evolving with that same noise constant. I also created a plot samples which plots the best samples of the data set. Best 64 samples of the data set drawn from a random distribution of 1,024 samples. All right. That is about it. That is all I have. Again, my name is Jaron Kelleher. Thank you for watching, and I hope you enjoyed this study and learned from it. Thank you.